Hello everyone and welcome to Signals, Systems and Signal Processing with Wolfram U. The topic of this lesson is Discrete-Time System Response. A system response is the sequence that is observed at the output of a system in response to some non-zero input sequence. In this lesson, we will look at system responses that are defined based on the type of the input sequence, namely unit sample response, unit step response, and sinusoidal response. Discussing the unit sample response, we will consider cases where the defining difference equation for the system is either recursive or non-recursive. Depending on the length of the system's unit sample response, we will have the infinite impulse response or IIR systems and the finite impulse response or FIR systems. Finally, we will look at two different components of the system response defined as the zero input response and zero state response. Recursive systems are modeled by a difference equation in the form shown here. The output at any given time n depends on its past values. For a system in general, the impulse response of a system is defined as the output of the system when the input sequence is the unit sample sequence, delta n. Now, to find the unit sample response of the system, once we have the nth order difference equation that models the system, we solve the difference equation with the input sequence set to 0, basically finding the homogeneous solution of the difference equation, with a time-shifted set of initial conditions that will contain y at time 0. So the problem now becomes solving the homogeneous difference equation with this new set of initial conditions. Recursive systems usually have unit sample responses that are of infinite duration. For this reason, they are called infinite impulse response systems or IIR systems. Let's look at an example. A system is modeled by the difference equation and with the initial condition shown here. We are interested in finding the unit sample response of this system. We start by finding the value of y at time 0 using the difference equation and the initial condition. Simplifying this expression, we get 4/3 for y at 0. Now, using the Wolfram language, we can simply solve the homogeneous equation together with the new initial condition and get the unit sample response. And we can also plot the sequence to see how it changes over n. As you can see, for negative values of n, the unit sample response of the system is 0, and for positive values of n, as expected, we have a decaying exponential. We just looked at recursive systems or infinite impulse response systems. Now consider a system that is modeled by a non-recursive difference equation. No past values of the output presented in the difference equation modeling the discrete time system. And y of n only depends on the input sequence x of n and its shifted versions. Following the same steps that we just discussed, assuming that x of n is equal to 0 for values of n that are less than 0, the initial condition at 0 can be obtained using the difference equation, replacing n by 0. Y at 0 is equal to b0. In the same way, we can find y at 1 up to y at capital N. After that, for n plus 1 or larger, the output response will be 0, and the unit sample will be of length n plus 1 in this case. We have a finite impulse response system or FIR system. Another important type of system response based on the input sequence is called step response. The step response of a system is the system's output when the input sequence is a constant function or a step sequence un. As an example, given the difference equation and the set of initial conditions shown here, let's find the step response of the system. Using the Wolfram language, we can get the step response easily, as shown here, and we can get a discrete plot of the step response to see how it changes over time. The first order and the second order systems, especially the second order systems, are very important in the study of LSI systems, as they could give us an idea about the behavior of higher order systems. Let's consider a second-order system defined by a pair of distinct complex conjugate characteristic roots R1 and R2 as given here. With these characteristic roots, the characteristic equation will be as indicated here, and we can also get the difference equation modeling the second-order system. Now, assuming that the system has zero initial conditions, let's look at the step response of the system for varying locations of the two roots. As you can see, when rho is equal to 1, we have persistent oscillation. The amplitude is constant. And when poles fall outside the unit circle, shown in red here, that is when rho is greater than 1, the step response is unbounded, and the system becomes unstable. For poles inside the unit circle, the system is stable and the step response decays over time. We initially have some oscillation, but it dies over time. The next type of system response that we cover in this lesson is the sinusoidal response. The sinusoidal response is the response of the system at rest to the sinusoidal input sequence sin of n. As we mentioned before, sinusoidal sequences have a very useful property, and that is that they are eigenfunctions of the LSI systems, linear shift-invariant systems. As we will see later, they are very useful for getting insight about the behavior of the system as a function of frequency. Let's look at a quick example. Consider the difference equation with the initial condition shown here, and let's find the sinusoidal response of the system. With the use of Wolfram language, we can solve the difference equation and get the sinusoidal response. And if we plot it, we can see that, in fact, we have a sinusoidal, as expected. When analyzing the system response, we could also look at two alternative components of the system response. These two components are zero input response. As the name suggests, it is the response of the system when we have zero input and some non-zero initial conditions. And the zero state response, the response of the system with zero initial conditions, that is zero state, and some non-zero input sequence. Let's look at an example to better understand these two parts of the system response. Given the first order difference equation and the initial condition shown here, let's find the total response of the system and identify its two components, the zero input response and the zero state response. Solving the difference equation with Wolfram language, setting the input sequence to 0 and keeping the initial condition as is, we can find the zero input response. Plotting this response, we can see that it starts at 1/3 and decays exponentially until it reaches 0. To find the zero state response, we keep the input sequence and set the initial condition to 0. This is a growing exponential which starts at 1 and goes to a constant value for larger values of n. Adding these two responses will give the total system response. Let's plot the total response together with these two components. The total response shown in green is close to the zero state response, but it starts at higher value and goes to the steady state at 3. In this lesson, we defined the system response, reviewed recursive versus non-recursive difference equations modeling the system, and defined finite impulse responses and infinite impulse responses. We then looked at different types of system responses based on the type of the input sequence, starting with the unit sample response and then the unit step response and sinusoidal response. We finally looked at two components of the total response, the zero input response and the zero state response.